Hearty welcome to all of you to today's episode of our online problem solving session for JAM and NET aspirants. Today we have Harinarayanan with us. He has completed M.Sc from now doing Ph.D. at IISER Tirupati.
Yeah, so my name is Hari, and as I'm also a mathematics student like everyone. And yeah, I'll be talking mostly about some basic analysis. I've seen that most of the universities have their exams and all going on, so I've tried to keep them simple, short, and yeah, and I have around 15 questions, and it won't be like we'll be doing some theory first and then questions. We'll see the questions and we'll discuss. You guys can let me know if you have some ideas. Of course, every question have more than one way to answer, so we'll see. I would like if there is some discussions. Okay, is that fine? And I'll be
Yes.
okay, thanks. And I'll be checking the chat section in between, and if I'm not seeing it, someone can please let me know if there is something. And I can see that there are around 50 people here, so everyone can help each other there also. Okay. So, and second one is differentiable. F is differentiable and derivative is bounded, and we have to check if it is uniform continuous. And third one, we have that it goes to 0 in the infinity, I mean in the ends, and we have to check if it is uniform continuous in all the cases. So any idea how to go about? Okay, let's start with first one. Let's say F is bounded implies F is uniformly continuous. Is this true? Answer in chat, or you can unmute if that's how it's going.
But false statement here.
Okay, so it is false statement. Why is it false statement? Do you have a counter example? Huh? Okay, so as I was saying, someone told me that this is not true.
Many of them have commented examples in chat box.
Oh, okay. Sorry, as I was out, I couldn't see it. So, okay, are they right? So we got a continuous function which is bounded, which is not uniformly continuous. Is it right? Sorry, I couldn't see any chat answer. So I suppose everyone got it. So yeah, so we see that this is not true. And one of the examples which you may have given is something like sine x square or something, right? Sine x square or sine exponential of x, which is not uniformly continuous, but it is continuous and bounded. Okay, now let's go to the second part. F is differentiable and f prime, this is essentially the derivative of s, is bounded. So does this imply uniform continuity? Hello, am I audible?
Yes.
Okay.
Yes, sir.
Yeah. Okay. So we have a function which is differentiable, which is given to be differentiable, and I know that derivative is bounded. So can I somehow say that it is uniformly continuous, or do we have an example where it satisfies the condition, but it is not uniformly continuous? Okay, so as I'm not getting anything in charts or audio, let's just see what the definition of uniform continuity is.
Okay, participants, you can respond to the questions.
Yeah.
You can either unmute and say directly, otherwise you can type in chat box.
Yes, you can do both. I'm keeping the yes. So Epic Life is telling that it is true. And why is it true? I mean, I'm not saying that it is true. Okay, so I'm just asking why you are saying it is true. So, okay, so let's see what is. Okay, you have already put. Yeah, so Anne-Marie is saying Lipschitz condition. So what it is saying is, I have that you have this mean value theorem, which is like f of b minus f of a by b minus a will be equal to sum f dash of c such that c is an element of ab or ba, whichever it is condition. Hence, you already know that f prime is bounded. Hence, I can do this. Assume the bound to be some k. So I can bound it by k. Hence, you will get that fb minus fa, which is essentially less than b minus a times k. So this is Lipschitz continuity, as Anne Marie have pointed out. Hence, you have uniform continuity. Yes, nice. Okay, now what about the third part? You have a continuous function, and we know that as it goes to infinity, the function goes to 0. Yes, Samrat Maji is saying Lipschitz condition. I suppose that's for the option 2, right? Samrat. Okay, yeah, I suppose he's saying that for the option 2. So let's go to option 3. If you have any confusions, of course, you can stop and ask. It's fine. So now we are discussing option 3. Do we have a continuous function which goes to 0 as mod x goes to infinity, but it is not uniformly continuous? Okay, so there is no replies. Okay, C is true. Why is C true? What we are, let me ask a simpler question. I have a function from, say, some subset of x, say A to R, and I can write this A as some B union C into two different subsets. Assume they are two intervals. So for example, let A itself is R and B equal to, say, minus infinity comma 0 and union, say, minus 1 comma infinity. I somehow know that if I restrict f to minus infinity 0, function to, if I restrict f to minus 1 infinity, this interval, I still have f is uniformly continuous. So can I somehow use the uniform continuity in these two things and say something about the whole function or the function from R, the whole set? Is that possible? Is that always possible? Is there some times when it is possible? The since the function existing in extended real number and also everywhere continuous, yeah, so I think what, I don't know, you can do that in B.Sc. Okay, talking about going to compactification of R and also let, I mean, that is, you are not wrong, you are right. Easier things. Okay, so Skinand is saying that you can do this essentially if we have two sets. I mean, here we have such that it is a function is uniform restrictions. Then he is saying that, yeah, by that f is uniformly continuous. So let's keep that in mind. This is you guys can try it out. And using this, can you now talk? into compactification to extended real numbers and stuff. Or am I confused? So should I just give one more hint, or should I answer the question? What would you prefer? I would really like it if it becomes a discussion, that way there may be other nice ideas which everyone will get to know. Just like Samrat said, it's a nice idea. You can see it as a function on compactification on far, and that's a compact set, hence it is uniform continuous. That's fine. But we don't want to go there. So okay, so I suppose no one is answering. So let me give one more idea. So this is not that hard. So what we are trying to do is you see how the function looks like. So the function will be like, this is my axis, and my function will go to 0 when it is minus infinity, and it may do something here. We don't know what it does here, and again it goes to 0, right? So this is what is going to happen. So what we'll do is we just cut it off in some point. So for example, as it goes to 0, I can find some natural number n in n such that if mod x is greater than n, I will know that f of x is strictly less than epsilon. Modulus of f of x is strictly less than epsilon. This comes from the definition that f goes to 0 as the function goes to infinity. I can do this. And if I'm, so that is like outside this particular thing, I have that it is very small. It is negligibly small. Right, and inside I'm taking another closed set such that here we have a closed and bounded interval. So one, I have this set, and second, I have a closed and bounded interval, which is like, I can say something like n minus, okay, minus n minus 1 to n plus 1. I can consider this closed interval, and I know that if I have a closed and bounded interval and I have a continuous function on that interval, I know that the function is uniformly continuous. Is that fine? So here I have that the function is uniformly continuous, and here also, as it is less than epsilon, then whatever x and y I take, I don't have a problem. X minus y, if x minus y is less than delta, we don't care what delta is. We know that f of x minus f of y is anyway less than epsilon. If I take this epsilon as epsilon by 2, then I can keep it as epsilon. So, which means that here also the function is uniformly continuous. So combining with our previous theorem, I can say that the function is uniformly continuous. Is this fine? Am I clear, or is yeah? Okay. So I heard a sound, but I couldn't hear it fully. You can write in chat, if you have a doubt, or you can open your, unmute yourself and talk. Okay, so I hope it is fine, and I'll
Okay, this is clear. In your second part, if we slightly change it, Can you find an
Okay.
example of a uniformly continuous function with unbounded derivative?
Excuse me?
A uniformly continuous function with
Huh?
unbounded derivative.
Um, yeah. Can you specify the domain? Are you restricting the domain somehow?
No, it doesn't matter.
Okay. So you want a function which is uniformly continuous but have unbounded derivative. Yeah, of course we can find it. So can any participants have any idea? I mean, can anyone try to answer this? Harshita, right? Okay, my claim is that yeah, it is possible. So uh, does anyone have any example for that? Okay, is the question clear to everyone in the first place? So her question is, I have a function f from R to Ri, and I f dash, f is differentiable and f dash is bounded. And I want to say that be uniformly continuous. Okay, so Akhil is saying, okay, instead of 0, yeah, so Akhil already gave an example. It says f from 0, 1 to R, you consider square root of x. X goes to positive square root of x. You can see that the derivative will be essentially minus 1 by root x or something. And that is, of course, unbounded as x goes to 0. Right, nice. Okay. So this is possible. Is there any more questions, doubt, or more to discuss? So everyone is fine with, yeah. So take log x in 1 by 2 infinity. Yeah, log x in 1 by 2 infinity works too. Yes, nice. In 1 by 2 infinity. Okay, how does log x in 1 by 2 infinity? Sorry, that is my mistake. Log x in 1 by infinity may not, 1 by 2 infinity may not work, you know. The function is like this. The derivative is what? 1 by x, right? Derivative of log x is 1 by x. And this blows up when x goes to 0. Whereas we don't have that part in our function. So Samrat, you can actually do something and make this using that, but log x may not work. Or am I wrong somewhere? Did I mess up somewhere? X squares, yeah, x square sine 1 by x. Nice. X square sine 1 by x. Why is it? Its derivative will be control D. So I have x square sine 1 by x. The derivative is what? 2x sine 1 by x plus sine ka derivative is cos 1 by x. Oh, 1 by x ka derivative minus 1 by x. Yeah, okay. Yeah, that works too. So x square sine 1 by x also works. Yeah, it makes sense because you have the function to be like this. And here you can see that the derivatives actually goes haywire. So yeah, that's a nice example. Okay, so shall we move on to next question or is there more to discuss?
सर sin x square का डोमेन कहाँ है इसका x square sin 1 by x का?
X square sin 1, you can take the whole R, you know.
Yes, sir.
It's not uniformly continuous. Oh, it's yeah. I mean, instead of that, you can actually put it like -1 to 1. Yeah, nice question. So -1 to 1, it is a continuous function in compact set, hence it is uniformly continuous. But as it goes to 0, its derivative goes haywire. So that works. Thank you.
Sir,
Thank you.
x square sine 1 by x is uniformly continuous in whole R.
No, no, no. I said -1, 1. I just take a
Yes.
closed bounded interval.
Yes, sir. Yes, sir.
Yeah. I mean, because x square actually makes the uniform continuity go haywire when it goes to infinity. So it won't be uniformly continuous everywhere. As it goes to infinity, it becomes not uniformly continuous. That's fine.
Sir,
Nice.
log x is not uniformly. उसका reason बताइए ना.
Okay. Oh, what log x is?
सर मैं वो जो एग्जांपल दिया था log x
हाँ.
का.
हाँ, log x. Why is it uniformly continuous? Is it uniformly continuous?
Yes, sir. Open A and infinity uniformly continuous है.
Closed a infinity में uniformly continuous है. Is it?
Yes, sir. Yes, derivative तो वो open A and half part तो unbounded है.
Okay. What's the derivative of log x?
1 by x.
Log
sir.
x derivative is 1 by x, right? You have given that log x in the domain 1 by 2 to 1 by 2 infinity, right? You already
Yes.
have that 1 by x is a decreasing function. So the maximum
Yes,
of
sir.
derivative is at 1 by 2, right?
Oh, okay, okay, sir.
Yeah.
Understand.
So essentially here you have that derivative is bounded, hence it is not uniformly. Hence
ठीक
it
है,
is
okay, okay,
uniformly
sir.
continuous. Yeah. Okay. So shall we? And you can call Hari. Okay. So no need to call sir. So okay. Anyway, so shall we go to our next question? This is a nice question. Okay, so we will move on to our next question. So this is a claim. This is asking you to give some examples if it exists. So I want a real continuous function which takes every real value exactly once. That is your first task. Second thing is every real value exactly twice and every value exactly thrice. I'm not claiming that all of these are possible. It may or may not be possible. So your task is to find which is true, which is not. Okay, as usually teachers do, I'll do the easiest one. So I claim that this is possible. So I can find a function from R to R, f from R to R, such that every value is attained once. So I consider f of x equal to x. So now the hard part is yours. Any idea? Any comments? You see, if you have some ideas, please don't hold back. Please talk. It's these are the places where you can express yourself and you can share your ideas. It's nice. Especially when you guys don't have classes and all. It's a nice place to discuss, you know. Okay, so Samrat is saying that B is true and Sheetal says that f of x equals x square gives an example for 2. Okay, so there is, and Rari is also saying that 2 is true and Reshma is saying 2 is false. So there is a clash. Okay, let me come to Sheetal's comment first. F of x equal to x square. So you can already see that you don't have any value which takes -1, right? I can't have f of x equal to -1 anywhere if I'm taking f of x equal to x square. Okay, I'll put G. So it doesn't take every real value, you see. So 2 may be true, but gx equal to x square cannot be a example for that. And Nimmi is saying that 3 is true. Why, Nimmi? can you justify your claim? You can unmute and talk if I mean, there is no point in typing the whole thing. You can. Connectedness will make 2 and 3 false. No. I mean, how would, okay, let me look at the question again. I'm saying that continuous function which takes every value exactly twice or thrice. How would connectedness affect it, Abhinand? Actually, it may affect, but I can't see how. I mean, connectedness is where if you can write it as disjoint open sets, singletons are connected in R, okay, fine. So inverse image of connected sets may not be connected. So image of connected set should be connected, Abhinand. So as it is a function, that is fine. Images are either 2 or 3. You mean image? Okay, number of elements are 2 or 3. No, you see, it is a function. So as it is a function, one element only goes to one particular element. So image only have one element, right? F of x equal to y. So this is a fixed thing. Once I fix x, I have y fixed, right? Yes, yeah, that's fine. That's fine. Happens. Okay, so Nimi, let's go back to Nimi. Nimi, you said 3 is true. Why? You can unmute and talk, unless you have a mic issue.
Hello, sir.
Yeah, hi.
Sir, if we draw a function's graph, considering the function as going 2 units up and 1 unit down.
Okay, so let me help you by drawing it. So I want a function which goes 2 units up. 1 unit, 2 unit up,
and 1 unit down.
Okay.
And if we consider a straight line along a y-axis.
And I'm considering
horizontal
straight line along y-axis.
Horizontal line parallel to x-axis.
Okay. Like this? Am I doing it right?
You can draw straightly.
Okay, am I doing it right?
Also, negative axis also.
Negative axis also. So it will go like say.
And I think that horizontal line touches the graph 3 times.
Horizontal line. You see, horizontal. Once you say horizontal line, it have a cardinality uncountable, right? So there is. You cannot say 3 times.
Okay.
But actually, you are getting very near to an example that I have. So nice.
Sir, question समझ नहीं आया. Sir, please question का समझ दिए ना.
अच्छा, एक और बार बताता हूँ. So हमें क्या चाहिए? हमारे पास एक फंक्शन है और its property is like this function is from R to R, right? अभी मैं क्या कर रहा हूँ? R का एक एलिमेंट ले लिया. So say pi. And if I'm considering f inverse of pi, I will have the cardinality 3. Cardinality of f inverse pi equal to 3. This is true for every real number. For example, in case of 1, I told that fx equal to x. X equal to x ले रहे हैं.
Sir, cardinality 2.
हाँ, yeah, continue.
Sir, मैं cardinality 2 के लिए f r2 close 0 infinity के लिए f of x equal to x square ले सकता हूँ?
Actually, I want from R to R, not from 0 to infinity. I want the whole R.
ठीक है sir.
Okay.
Hello?
Yes. Yeah.
Like, can we have a graph that takes like a shape of n, then an n, like what we say?
Shape of n.
Okay, then from the top take an n again. From the top of this n. Nice.
So you as yeah, nice graph. So, Oh, sorry, I was unable to hear you. So, can you repeat? I heard a sound.
Exact types. Sir,
Yeah,
exact
exactly.
type.
6. Let me draw it again. So, and in the end, I'm putting one more n, repeating then this n to if it passes exactly, which means every point, if I put this n properly, even in this corners, I have three points exactly, right? Is this what you meant?
Yes.
Yes, nice. So we got an example for 3. So we got that 1 is true, 2, 3 is true. Now all we are remain, I mean, all it is left with is 2. Can I find a function such that its value is taken, every real value is taken exactly twice? Every value taken exactly twice. A mode function. Okay, as it says, mode function, it can only take positive values, right, Sheetal? I cannot have any negative value there. And even 0 is taken only once. So okay, so 2 examples, although, yeah, so Sharanya is saying that it doesn't exist. I suppose someone else also told that it doesn't exist. Who was that? Let me check it. Oh, Nimmi. Yeah, Nimmi and Sharanya are saying that it doesn't exist. Why, Sharanya? I mean, 1 and 3 exist. What's the problem with 2?
Sir, we can prove this using intermediate value theorem.
Nice. How?
If we consider an interval 0, a.
0, a. I'm considering. Can I take closed interval, Nimmi?
Yes, closed interval, sir.
Okay, thanks. Yeah.
Then by maximum minimum theorem, it must have that function must have same maximum and minimum value.
Okay, say the maximum is small m and okay, maximum is capital M and minimum is small m. Okay.
And if we take a point C which belongs to this interval 0, a.
Okay, I'm taking C from 0, a.
And endpoint D outside this interval.
I'm taking D in the complement of A. Okay, fine.
Then these two points must have the same value.
Come again.
That your screen is
Hari,
visible.
presentation is gone, not visible now.
Oh, okay. Sorry, something happened maybe. I'll. I'm sorry for that. Is it visible now? Is it fine now? Is it visible now? Hello?
Yes.
Yeah, thanks.
Yes.
So I have written that C is an element of closed 0a and maxima is capital M, minima is small m. And I'm taking some element from the complement and one element from inside. So, Nimi, can you continue?
Sir, and if we plot a graph, just
Okay,
a curve.
Okay, you want what kind of curve do you want? Something like a parabola or
just like a which touches the y-axis, not x-axis, not
it
touching the
touches.
x-axis.
Okay, okay like this.
Okay, sir. But if we take 2 points, it touches the horizontal line 3 times, but we want only 2 times, and it becomes a contradiction. I think so.
Okay. Oh, okay. Where does it touch 3 times? It's only touching 2 times, right? And here it is touching once. I mean, this more or less looks like x square. Actually, your idea is right. I mean, as far as I know, and I have an answer in my mind. So that idea is almost same. So Yeah, okay. So is there something that I'm not understanding here, or did I draw the graph wrongly or something? Hello, am I audible? Did I get out of the presentation? Sainul Abid is saying why. Hello?
Yes, sir. You are audible, sir.
Okay, thanks.
I think, sir, maximum and also minimum, then I think it will intersect the x-axis at most 1. So we will get a constant function. So I think second is not true.
Okay, so let's just take this graph and consider this. She was talking about A0A, right? I have 0A, and this is my 0 and this is my A, and my minima is this and my maxima is this. Now I wanted to take an element from 0A, so let's take this is my C and this is my D. So image of C is somewhere here and image of D is somewhere here. And Nimi, you were talking about something intersecting 3 times.
Sir, if you draw a curve which touches the graph 3 times, then it will be contradiction. I think so. I'm not sure about that.
Okay, I'm actually unable to understand what you're saying. Somehow I'm skipping something. I mean, I put a C here and a D here, and I can't really see anything which is striking 3 times, right? We can only see twice. This is being taken once here. This is being taken once here also. So both are taking twice. But the problem is nothing here is being taken. So that's a problem with this graph. So okay, is there any other idea? So what I know is almost like what Nimi said. Is there any other idea? Otherwise, I'll share what I know. Okay, so let's go to what I know. Just as Nimi did, I'm also gonna take a closed interval, say, or before taking closed interval, I assume that such a function exists. F have the desired property, which is like every element is assumed exactly twice, right? And I'll randomly choose an element, say 0 in R. As I have 0 in R, I know that I have some x1 and x2 such that f of x1, this is my greater than x2, and you are seeing this particular interval x1 comma x2. Like Nimi was saying, I can maxima and inside this assume that maxima is some capital M, minima is, and I know that 0 is somewhere in between M. Right. So it is possible that 0 is maxima or 0 is minima. If 0 is maxima, you check the minima. So you take something which is not this thing. Okay. So I just take the minima. Assume that M is minima, and if 0 is maxima, 0 is already being assumed twice. So 0 is maxima. Just assume for now, doesn't really matter. Then I consider M. M is being attained once inside the interval, at least once inside the interval x1, x2. Can it happen? Can it attain twice? Can M be attained twice? Okay, twice in x1, x2. Are you clear till here? Yeah, epic life is saying we can always find there is a function that have 2n plus 1 values. Yes, true. You just make that n into as many times as you want. So yes, nice. Yeah, then x1 equal to x2. No, that is not necessary, Sainul, because we have already taken them to be different. And I'm assuming 0 is the minima. 0 is the maxima. Okay, so m is minima. Sorry, my mistake. So can the minima be attained twice? So 0 is the maxima. So it is something like this, right? I have, this is my 0. If 0 is maxima, then I should have something like this, right? So this will be my minima, m. I'm saying that m cannot be taken twice inside this interval. My claim is, assume it is taken twice. Then what will I do? I will choose those points. If it is taken twice, it will be something like this, right? Should be something like this. M is taken twice. Then I'll call these points some C1 and C2. And in C1 and C2, I know that if I consider a ball here, I can have things which is being assumed 4 times. So this is what I'm trying to do. Is my idea clear to everyone?
Sir, can you please repeat it once more?
Okay, from which part?
Can M be attained twice in the interval?
Yeah, exactly. So can M be attained twice in the interval? You're okay till here, right? Till here you're okay, I suppose. So I'm checking the possible twice. So can M be attained twice? This is my question. Be attained, right? So this graph is just for our understanding. Okay, so this is not part of a proof. This is just for our understanding. So assume that M is being attained twice. So my idea is that, so M is being attained in these 2 points, right? And if I consider just something which is just above this M, can you see that it is being attained 4 times at least? I mean, these points. Hello, am I audible?
Yes, sir.
Yes, sir.
Okay, so is my argument okay? Can you see that it
Yes,
cannot be attained, it cannot be taken twice inside the interval? I know that it is attained once. If it is attained twice, I know that it will be some value less than M will be attained more than twice. I mean, all I have to do is you take this smaller interval. So assume this is C1 and C2. And in this C1 and C2, I know that this M is minima. In C1, C2, I know that M is minima. M is minima because C1, C2 is subset of x1, x2, right? Then I can talk about maxima. So maxima is some M1 and will be less than or equal to 0, right? So what I can do is I have x1, C1, this is one interval, and I have C2, x2, this is second interval. So every value between 0 and M1 will be assumed here once, assumed here once. And moreover, we already know that this endpoints, the value is small m. So I know that not only m, I have 0 is maxima, 0 m is attained. And as I have that m is less than m is minima, right? Okay, am I being too confusing? Jyotish is saying yes, sir. Are you replying to my question of am I too confusing? Hello, am I audible? Can everyone hear me?
Yes, sir. You can continue.
So, is it clear when I said that some point will be assumed more than twice?
Yes, sir.
Yeah. So this essentially says that m will not be assumed twice inside the interval. So which is to say that m can be assumed once outside, right? So what will happen? We'll just go back to the graph again and see what may happen. So this is my first point and this is my minima and 0 is the maxima here. And I know that this is attained once more somewhere here or here, doesn't matter. So I'll assume that it is assumed to the right side. If it is assumed to the right side, it should somehow come like this, right? Which means every point between 0 and this minima will be assumed thrice, not twice. Is that clear? Here we are again assuming, considering intermediate value theorem. Being said is I have x1 comma x2. Here image will be some small m to say 0 or something greater than 0. And after x2 to there is some point where this minima is attained again. I call it x3. In x2 to x3, I have minima being attained. Hence, I have that every point between 0 and this minima attained 3 times. So once here, actually twice here and once here. Is it fine? So in both cases, I am saying that you cannot have a function which assumes every value exactly twice. Is it clear? Should I repeat or should we keep it for a discussion time or something? You can ask me more doubts if in discussion time. Can I continue to the next question?
Yes, sir.
Okay, so okay, thanks. So yeah, so now this is a after a question which took a long time. Let's see a relatively simple question. So we have fn and gn to be continuous functions. Continuous doesn't, yeah, continuous functions which are converging uniformly to f and g. Right. So I have fn uniformly converging to f, gn converging uniformly to g. So I'm asking, is this true? Fn plus gn converge uniformly to f plus g. Is this true? Okay, everyone know the definition of uniform convergence, right? Is everyone familiar with the definition of uniform continuity? Sorry, uniform convergence? I'll take that as a yes, I suppose. Okay, so
Yeah, you can
Pradeep,
accept it.
okay. Okay, so I assume Anashra and Pradeep are saying 1 is true. Okay, let's keep it at that. We'll see the proof if necessary. And Mridula is saying that 2 is false. And she's saying x comma x. What is this x comma x, Mridula? Okay, you are assuming. I want a sequence of functions which second is true if and only if f and g are bounded. Nice. Yes, so you essentially gave the idea. Mridula, you are right actually, you are not wrong. So
Sir.
you can consider fn to be equal to x, which obviously converges to x itself, right? And gn to be again equal to x, which again converges to x itself. Both are uniformly continuous, both are converging uniformly. And fngn, in this case, actually it converges uniformly. Sorry, yeah, Mrudula, my mistake. Actually, this gives you another question. So x is uniformly continuous, but the product is not, you know. So you have some other example there, but let's not go into that. Okay, so Pradeep, can you give me an example where this fails? Fn and Gn are uniformly converging to f and g, but f dot g doesn't converge uniformly. Pradeep Mishra? Yeah, Mridula, I got that, and I too thought it so. Pradeep, are you around? You can unmute if you don't want to type. Okay, so I'll give an example as Pradeep is not giving an example. Okay, assume function f to be x itself. Let fn equal to x and which converges to x. And let gn to be equal to what? I can consider it some 1 by n. Right. So this 1 by n converges uniformly to 0. These are constant functions, right? Constant functions are uniformly, constant functions converges uniformly to 0. That is fine. Now what happens to the product? Product is fn gn is equal to x by n. And you know that it actually converges to 0, but pointwise at least. Because given any x in R, I know that x by n converges to 0. That is fine. So this converges pointwise, but it doesn't converge uniformly. Is that clear to everyone that x by n doesn't converge uniformly to 0? Because if I consider say xn equal to n, then I have fn gn of xn, which is equal to n by n equal to 1. Right? This is a constant sequence 1, which doesn't go to 0. So I have a sequence such that image of the sequence doesn't go to 0. Hence, you know that the function fn gn is not uniformly convergent. Is this fine? Okay, so Anne-Marie is saying okay. So shall we move on to the next question? Was it too easy that no one is responding? Okay, well, it's possible. Okay, so we'll go to the next question. Oh, nice. Okay, so this is a if I consider fx equals x square and gx equals x cube, you need some function which you need a sequence of function converging to x square and x cube, and then somehow say that the product doesn't converge uniformly, Pradeep. Okay, so let's come to next question anyway. So, the question is like you have a continuous function from q to q. They're asking, do you have a okay, let's see something else now. Assume I have a continuous function g from R to R. Right. As I have R, I can just restrict it to Q. So I can restrict it to Q to get a continuous function from Q to R, right? So as it is a restriction of continuous function, I know that G is continuous. So the question is the other way. I have a continuous function in Q from Q to Q. Let's say instead of Q to Q, let's just take Q to R, doesn't matter. So assume I have a continuous function from Q to R. Can I find a continuous function from R to R such that its restriction is F? This is the question. Is the question clear for everyone? Hello, am I audible?
Clear, sir.
Yeah, so is the question clear to everyone? Yeah, okay. So it's not, why are we taking Q? You know that Q is a dense subset of R, you know, Q is a dense subset of R. So Q closure equal to R. So we actually have that you can, when you are in nice circumstances, you can actually do it. But here you only have continuity. So they are not randomly choosing a function. I mean, this comes from a proper background. So please don't think I'm randomly putting questions. So makes sense, right? If I have okay, so the question is clear. And what about the answer? What do you think? Is it possible to have a continuous function, or is it not possible? If it's possible, we need the justification. If it's not possible, we need a counterexample. Okay, for constant function, it is possible. Yes, for constant function, you can just at Q to R, if I'm taking it to be a constant, I can define the same constant to be in R, hence it is possible. And Akhila is saying that it is possible. Can you elaborate, Akhila? You can turn on your, unmute your mic and talk, you know. Only continuous function from Q to R is constant. Reshma, why is it so? I mean, uniformly continuous function can be extended. Uniformly continuous function. Yeah, that is true, Abhinand. But Reshma, for example, assume from G from R to R to be sin X, and you just restrict sin X to rationals, or just consider G of X equal to X, identity function. And if we restrict G to Q, it is continuous, right? It's fine. Okay, so are we in a consensus that it cannot be done? Because Reshma is saying only continuous function, which means to say that she have a continuous function from Q to R, which is, okay, sorry, Reshma is saying only continuous functions are constant functions. That is not true, Reshma. We can consider the identity function from Q to R. Okay, from R to Q. No, we are considering from R to R, so that's fine. Yeah, okay. So Abhinand is saying uniformly continuous functions can be extended. So Abhinand, can you give me a function from Q to R which is continuous from Q to R, but cannot be extended to a function from R to R. You can turn on your mic if necessary.
Sir,
Hello? Yeah.
yeah, here Q is, I don't know whether it is true. I'm just studying.
Yeah,
Here
that's
Q
fine.
is dense in R.
Q is dense in R, true.
Yeah. Suppose there is a function f from Q to R which is continuous.
F from Q to R, which is continuous. Okay.
Yeah, now the remaining is only irrationals.
Yes, irrationals.
So if we take any irrational number, we can
Okay,
find the rational sequence converging to that irrational number.
Okay, so let's say Qi are rational sequence and okay, Qn converges to R. Now?
Yeah, since f is continuous,
Huh?
f of Qn converges to f of R.
F of Qn okay, I'm writing it, okay. I'm writing f of Qn converts to f of R. There is a question why this happens and why this even makes sense. And yeah, please continue.
Yeah, I stuck. Sorry, sir.
That's fine, it happens. So you see, first thing is, why would f of Qn be a convergent sequence? That is first question. Why is f of Qn convergent? And if it is convergent, then it converges to some point. We don't know anything like f of R because f is defined on Q. Okay, so we don't have any function value on R. So the candidate for you to define the function value on R is this f of Qn limit. Yeah, that's fine. Is that what you meant?
Yeah, I was meant that.
Yeah.
So I think it can be extended to R.
Yeah. So so and as Anne Mary is saying, you are saying that you can define the limit to be f of Qn, right? That's what you mean.
Yeah.
Two questions. Why does the limit exist? One. Second question is one sequence which is converging to R. Assume you have another sequence, say Sn converging to R. What is the guarantee that f of Sn also converges to the same limit? You have to answer these questions, right? I mean, these two things are necessary, right? If you want to properly define the function value at a point, you need to make sure that it is unique, right?
Yeah. Yes.
Yeah. So these, I mean, these questions make sense, right?
Yeah. Yes, sir.
Yeah. So let's try to see. I'm not saying that you can extend, okay, because Abhinand is saying uniformly continuous functions can be extended, but he never said that a function which are not uniformly continuous cannot be extended. Okay, so keep that in mind. Or if Abhinand, if you have an example which is continuous from Q to R which cannot be extended, you can tell that way. Okay, you are not getting. Yeah, that's fine. That's fine. That's fine. Okay, I'll ask. You know the function tan x, right? Tan x. Hello? Hello, am I audible?
Yes, sir. Yes, sir.
Yes.
Yeah. So is tan x from R to R?
Yes, sir.
Is it continuous?
R2 interval minus pi by 2.
Sir, no, sir. Pi by 2.2 to sir discontinuity है.
Minus pi by 2 to pi by 2, it is continuous.
Plus pi by 2.
Right. Now,
Yes, sir.
now consider tan x from Q to R. Now what happens? We don't have pi by 2 anymore. Right. Now is it continuous?
Yes, sir.
It is, right?
It had no continuous extension in R.
Yeah, so that's a straight away thing. I mean, this is a function that you have seen, but let's see a easier example. Okay. Okay, so I am already claiming that this is not true. It's not always possible to extend a continuous function in Q to continuous function in R. So first thing you have to do is we have to actually get out of the notion of continuity in R, because when you say continuity in R, we tend to draw a graph without lifting our pen. That's what we usually do, right? Draw a continuous function in R. But Q is a very different set. So you consider a very simple example like this. Assume this is pi. Okay, so from minus infinity to pi, I am considering the constant function 1. And from pi to infinity, I am considering the constant function minus 1. I don't have pi in Q, right? I don't have pi in Q. So I am actually saved. So is this function continuous? What do you think? In Q, okay, I'll call this as some h of x. So is h from Q to R continuous? Yeah, so Mridula is saying no.
Yes, sir. True, true.
Saying yes. And
yes, sir. Pi true continuous.
Okay, and here, yeah, so we are getting a lot of yes and a lot of no. So actually this is continuous. Why is it continuous?
The pi point does not belong to Q.
Yeah, pi does not belong to Q. Yeah, exactly. So you can actually check that it is continuous. So all you have to do is inverse image of open set is open. So if I take an open set here, it is of course open singleton. If I take it here, it is 2 points, which is still open. So it is actually continuous. But here you had two questions, right? What is the problem here? Can f of qn converge to f of r? Yes, it actually converged. But if I'm taking one sequence from the left side and another sequence from the right side, you can see that the limits were different actually. Right. So, hello. So, who was actually giving this idea? Let me see. Anne Mary was saying that define GR to be a limit. So, like that. Yes. Yeah, if we were trying to do that particular thing, this is the problem. You see, you got two different limits in this case, right? And in case of tan, we saw that there is no limit. I mean, this doesn't converge. So we had two questions and we got two examples where both are being broken, right? I got an example where f of qn is not convergent, and I got an example where f of qn is convergent, but if I limits, fine. Hello. Okay, so if we were actually considering linear functions, then this would have been true in some case. Okay, let's go to the next question. Shall we go to the next question? Yeah, this is nice. Okay, so I have a function given here, x cubed by 1 plus x square. I want to check if this function is uniform continuous or not. What do you think? I mean,
Sir,
I suppose. Yeah.
domain.
Okay,
Sir,
take your domain as R. R to R. I suppose everyone have your pen and paper, so you can try it out and let me know. Or should we come back to it later, or what's the thing? We can do whatever you guys are comfortable with. Okay, I'll tell you the answer actually. You try to do that. That way it will be easier. It is actually uniform continuous. It is uniform continuous. So there are many ways of checking it. You can do one of it. You can even more or less see that it is Lipschitz continuous. Okay, so maybe I'll give this as a homework. You guys try to do it, and if not possible, you can get back to sir or someone, or you can ask me, whichever is fine. So shall we go to the next problem? You can take down this problem. It's not that hard. So it's just a computation problem. I put it in case someone is interested. So shall we move on to the next problem? We'll come back if we have time once we finish everything. Okay. Okay, I'll take that as a yes. Okay. It's again a justify or counter. We are defining something called a projection map. It is a map from R2 to R. You have two coordinates. You are projecting it to the first coordinate. So you are projecting it to the first coordinate. And the what you are asking is, if I am having a closed set C, okay, assume projection map to be P. So question is, if C is closed, is f of C closed? So C is a closed subset of R2, and this is a projection map. So essentially it is like this. Assume you have your coordinates like this, and assume you have a set here. For example, I have a circle here. Okay, it's a filled circle, assume. Then the projection to x-axis is essentially this. It will be this straight, this closed interval I'll get. Okay, and if I'm considering an open circle like this, open disk like this, then I'll get an open interval here. And if I consider a square, then I'll again get an interval. I mean, anyway, we are gonna get intervals and all. So I suppose you get the idea of projection map. So it's like you are assuming that you have a very big light source here, a big light source, and you are just talking about the shadow. And this is a very nice light source. The light only comes like this. It's not like we'll get light like this. So keep that in mind. Okay, so we want to talk about the shadows. Closed set. Is the projection of this closed set closed? Any idea? Comments? Suggestions? Hello, am I audible?
Yes, sir. Audible.
Yes, sir.
Okay, so did everyone understand what a projection map is? Hello. So is the projection map definition clear to everyone?
Yes, sir.
Okay. So definition is clear. And what is it that you feel? So if I have a closed set, can I have a, what can be the projection? Okay, you know what a closed set is. Yeah, Mritula, is closed set means I just have limit points of that set inside that set itself. Okay, so is the definition of closed set known to everyone? Hello?
Sir, can I tell?
Yeah. Yeah, of
Yeah.
course.
Yeah. So here we have to show that f of c is closed or not.
Yeah,
I'm trying
exactly.
to prove. Yeah, I'm trying to prove f of c is closed. So
Okay, so my claim is f of c
f of c
is closed.
closed.
Okay.
Yeah. So I'm taking a limit point a of f of c.
A of f of c is a limit point. Is a limit
Yeah,
point. Okay.
yeah, I'm trying to show that a belongs to f of c.
Okay.
Okay. Since
To
a
prove,
is a limit point of f of c, we can find a sequence an which in f of c which converges to a.
an in f of c such that an converges to a. Okay, fine.
Now an is in f of c, so we can find a sequence say yn in c such that f of an yn is equal to an.
F of an yn.
Yeah, because f is a projection.
You see, yn is a subset of c. This yn actually have two coordinates, you know that, right? Like y1n, y2n. Similarly, this a also have, a only have one coordinate, but this yn have two coordinates. You understand that, right?
Oh.
I mean, you are taking
sir,
c as a subset of R2.
No, sir. I am thinking that f of an yn is an. So since f is a projection, we can find such a yn.
Oh, sorry. So as it, okay. I get the point. As an is subset of C, you are considering a and yn to be your pre-images, a and yn.
Yes,
F
sir.
of a and yn equal to an converges to a. Okay, fine. Now?
Okay. Now an yn is in C.
Yeah, a and yn is in C.
Yeah. So and also C is closed.
C is closed.
So it will converge.
Okay, so I'll ask you a small doubt. Assume my a and yn is n comma n.
N is already converging to A, sir.
Okay, 1 by n. I mean, you know 1 by n converges to 0,
Yeah.
right? But your claim was yn converges, right?
Yeah.
But here yn doesn't converge, you know.
But
Okay, I mean, am I making sense?
yes, sir. But yeah. Okay.
Yeah. So good that you told this. The answer is actually no.
Yeah. Now I feel so.
Yeah. So yeah, that's fine. So what we'll do is we just this is essentially exactly this, something like this. You know the function f of x equal to any function like this. So for example, you consider f of x equal to 1 by x, right? The graph looks like this, right? Huh? This is the graph. So you just consider this one part of it. Just ignore the other. Where x greater than 0, you just consider. And you know that this is closed because whatever sequence you consider, it will converge to that point. So it is fine. This graph is actually closed, but the image is actually open 0 infinity. 0 is a limit point, but 0 is not in the projection. And it's exactly this which is happening. You have the sequence 1 by n comma n in my so-called image in your graph in your closed set, but this doesn't converge anywhere. 1 by n actually converges to 0, but n, as you know, goes unbounded. It blows up. So is this clear to everyone? Hello, am I audible?
Yes, sir.
Okay, so should I be explaining again? Is there someone who didn't understand and would like to understand? Okay, so is clear. Okay, so shall we move on to
Hello.
Yeah, hello.
सर ग्राफ का पोजीशन क्लियर नहीं है सर, रिपीट प्लीज.
Sorry. Hello. Hello, am I audible?
Yes sir.
Okay, so shall we move on to the next question? Yeah, I already have the next question.
सर इसका आंसर ट्रू है सर.
किसका आंसर?
न्यू आंसर सर, न्यू क्वेश्चन का आंसर.
Okay, f from
F
0
is
infinity
continuous
to
and
r
limit x
continuous.
to.
Okay, so
Yes,
you are
sir,
saying that maximum value, so claim is it is true.
True, yes sir.
Why? Can you give me an idea of proof?
Okay sir. Sir, this function is continuous and limit extends to infinity exists, so this function is also uniformly continuous. And
What?
so this function is continuous,
Yes.
and
Okay,
the
and you are
domain of the
saying that it
function.
is uniformly continuous. Okay, it is uniformly continuous. So
So uniformly continuous, it attains the supremum value of the function, the set. So this function is also
okay, so
bounded.
you have this function, right? F of x equal to x, which is the identity function. You know that it is Lipschitz continuous, hence it is uniformly continuous.
Yes, sir.
Yeah. So, but does it attain its maxima or minima?
No, sir.
Yeah. So the uniform continuity doesn't necessarily imply that it have its maxima or minima, right?
Oh, okay, sir. Okay.
Okay. But in this case, what can you say?
Okay, sir. I can try it.
Yeah, of course.
सर मैंने तो वो भी सोचा था, आपको जो बोला था.
अच्छा. ठीक है. That's fine. Abhinand is saying consider closed zero n. In closed zero n, you are saying the maximum exists. Yeah, that is true because we have a closed and bounded interval compact set. So you know that the boundary values are assumed. Okay, Abhinand. Fx equals 1 by n. Is it a constant function, Reshma? Or do you mean 1 by x? If you mean 1 by x, it is not a continuous function at 0. Reshma, do you mean f of x equals 1 by x or? Okay, Abhinand is saying for epsilon positive, there exists some natural number n such that modulus of fx is less than epsilon for every x greater than n. True. Balu is saying consider function like minus 1 by x with some modification, etc. Nice. So Balu is essentially giving a counter example for this. Okay, so what he have done is just his idea is this. We only know that it is continuous and its limit is 0. So what he is trying to do is make the supremum 0 and take a increasing function. For example, he is considering minus 1 by x. So minus 1 by x is this in positive part. It is something like this. But of course, this is not continuous. So what we do is we just shift it a bit and do it like this, so that we don't have to worry about this part. So it is a continuous function and this increases and the supremum is 0, but it never reaches 0. Right. So it satisfies the condition, right? F is a continuous function. It is continuous function and the limit is 0, right? The limit is 0. It goes to 0. But the supremum, maximum value, I mean, it doesn't have a maximum values, but the supremum of fx equal to 0, but 0 is not attained in 0 infinity. Is this what you mean, Balu?
Yes.
Yeah.
It is right.
Okay. Yes, nice. So Ria is saying, sir, is there any basic real analysis course from you? I'm sorry, I'm a student. I'm sorry, you don't have to call me sir also, but actually, no, sorry. Okay, but anyway, let's come back to this. So what Balu said is, yeah, True. So this works as a counterexample. Is this fine for everyone? Is this okay? Is this understandable? Okay, so Akila is saying it, right? Now this may be something which you guys have seen, something like this. So let's discuss this. So we are moving to the new problem. It says you have a continuous function which we know that is always greater than the function x cube. And you are given the integral of the function to be equal to 1/4. So what we have to claim is the function is actually x cube itself. This greater than part doesn't play a role. So we have that it is equal to x cube. So any idea in this direction? Hello, am I audible? Is my presentation visible?
Yes, sir.
Okay, thanks. Okay, you don't need to give the whole proof, or you don't need to give the whole thing, you can just, yeah, exactly. So Abhinand is saying consider the difference. So we consider fx minus x cube. From this inequality, I know that this is a non-negative function. Now what are you going to do, Abhinand? Yeah, integral is 0 because integral 0 to 1 x minus x cube equal to integral of fx in 0 comma 1. I'm skipping dx, okay, please don't mind me. Integral 0 to 1 x cube. And I know that this x cube have integral what? 1/4 x power, actually 1/4, right? 1/4 x power 4, where it actually becomes 1/4. And I know that this is also, here also I have the integral is 1/4. So it becomes 0. Right. Now you have a non-negative function whose integral is 0.
This function is must 0.
Yeah, exactly. So if what we are using here is if f is continuous and integral on a closed and bounded interval ab f equal to 0, this means f is identically 0 in AB. So this is what we are using, right? And I suppose all of you know the proof, because in the proof what we are doing is assume it is non-zero. So there will be some a such that f of a is assume greater than 0, because it's a non-negative function, so it can only be greater. So you just consider some epsilon neighborhood such that function value f of x is greater than epsilon, and you will get that integral is positive. Integral f is positive. So this is the basic idea. Is it fine? Everyone, I mean, I suppose all of you are familiar with this. So you are okay with this, right? Shall we move on to the next question?
Yes, sir.
To the next question. Nice. Okay, so we have a function from R to R. So, and it is a continuous function. And we are mostly worried about the image of this continuous function. So we have to see if the image can be 0, 0, 1, closed 0, open 1, closed 0, closed 1. So each of wherever you are saying, yes, this can be an image, you have to give an example. If you are saying no, then you have to tell why. Okay, so that's how it goes usually, right? Here we are assuming that f is a continuous function from R to R. Now After once we are done with this, I'll change the question like f is a continuous function from 0, 1 to r. Then I'll again ask these questions. Okay, so this is my plan. Okay, let's go. So start. You can give me examples or ideas. You don't have to give the full answer or anything. Yeah, so Ria is saying you consider f of x equal to 0. So f of x equal to 0. So here image of close 0, open 1 is singleton 0. Yes, so this can be a image. Okay, yeah, Reshma is also giving the same idea. Yes, true. Now for 3 identity map. Yeah, so here you are considering, for 3 you are considering f of x equal to x itself. 0, 1 is 0, 1 again. So this is also possible. Now you have 2 down, 2 more to go. You don't have to actually give the exact definition and all. Okay, 2 and 4 will contradict the continuity. Inverse image of open set is open and closed set is closed. Inverse image of you see, inverse image of closed set is closed and inverse image of open set is open. That is true. But it doesn't say anything about the image, right? Because when we are considering inverse image, inverse of C is actually what? Set of all x in R such that f of x is element of C, right? So for example, if I am considering say f of x equals x square, right? And you consider closed interval 0, 2. The f inverse of 0, 2 is actually minus 2, 2. Whereas if I just, okay, minus root 2. Okay, I'll take this as 4. 0, 4. So minus 2, 2. But if I consider zero to is equal to 0, 4, right? So yeah, which is not the image of 1. If 2 is true, then contradict. Inverse image of 0, 1 should be open. You see, that's what I am just saying, Ria. If f of 0, 1 is image, okay, you are saying 2 and 4, right? So 2, I can more or less understand where it is coming from, but why are you saying 4 is also not possible? Yes, f inverse may be something like this. Different, right? Of open minus 1, 2. Image is also right. So this is not a closed set. Minus open minus 1, 2 is not a closed set, but still the image is a closed set, you see. So it's not necessary, Abhinant. So, but as it goes, open 0, 1 cannot be an image. Okay, so we are actually done with 1 and 3. And from what example I have given here, you may have already seen that you can actually make 4 also, because let's say 0 open 1, right? Instead of writing exactly the equation, I'll just give you a graph which I hope will be sufficient. So I want a graph. Image should be close to 0, 1, right? Image should be close to 0, 1. So close to 0, 1 is this. So I'll do this. And this is my open 0, 1. I'll do something like this. For example, let's say x 2x square minus 1 by 2 or something. Doesn't matter. So what I'm doing is I'll take a graph like this. So here, if I'm considering open 0 close to 1, I'll get the images. Is this graph making sense to you? Or should I make a bigger graph? It goes like this. So the image is actually from here to here. This open doesn't really matter because it's actually image of this closed set. Am I audible?
Yes, sir.
And is that example clear?
Okay, sir.
Yeah.
Clear.
So what Abhinan, one thing you know about continuous function is, if I have a closed and bounded interval, okay, Akhila is saying she didn't get the example. So what I'm trying to do is something like this. So all I want to have is, I have this interval, right? Open 0, close to 1, or is it the other way? No, close to sun. Okay. Close to 0, open 1. I want that f of this equal to 1 close to 0, 1, right? This is what I want. So what I will do is, I will make a function. Okay, let's consider f of x equal to modulus of 2x minus 2x minus 1 by 2. Okay. So what happens in this? It is when x equal to 1, it is what? 2 minus 1 by 2. Okay, let's say minus 1. So that will become like this. No need for this. Actually, this will suffice, no? 0 at 1 by 2 itself, right? Yeah, you consider this function. F of x equal to 2x minus 1, modulus of 2x minus 1. Akhila? So what is f of 1? What is f of 0? F of 0 equal to 1, right? And f of x equal to modulus of 2x minus 1. And I know f of 0 equal to 1. And f of 1 by 2 is equal to 2 into 1 by 2 minus 1, which is equal to 0. Right. So I have 0, 1 is my interval. And inside this interval, I am assuming 1 and 0, which means closed interval 0, 1 is actually contained in the image. But actually, it turns out that it is an increasing function if I consider, if I split it from 1 by 2, and the maxima is always 1. 0 it is 1, f of 1 is also modulus of 2 minus 1 equal to 1. So this 2 minus 1 actually gives the example here. F of x equal to modulus of 2x minus 1. Is it clear now, Akila? Okay, so now all it is remaining is open 0, 1, right? The thing is, open 0, 1 cannot be an image of closed 0, open 1. Can anyone guess why? Okay, so I'll tell you why. So you may already know that if you have a function, continuous function f, then image of a closed and bounded interval, say a comma b, is actually again a closed and bounded interval c comma d. This you know, right? Because closed and bounded interval will be mapped to closed and bounded interval. Maxima is attained and minima is d. Minima is c. Intermediate value theorem between is also. Hello?
Yes, sir.
Am I homomorphic epic life? You mean they are homomorphic? Yeah, they are homomorphic, but F morphic. So what? Yeah, you have this property. It's a continuous function of open one, and closed one. So and assume that we actually had a function that closed 0, open 1 have image open 0, open 1. Consider image post particular know that closed 0 closed audible. Can you hear me?
Yes, sir.
Okay,
Yes.
and can you see my presentation? Yeah. So what I was saying is, assume that was true. Then if I just consider closed 0, closed 1, then the image should be closed 0, closed 1 again. We need a closed and bounded interval. Should have closed 0, closed 1. But I am only adding one more point. Point to this. But in the image, I need at least 2 more points extra, right? Am I making sense? Okay, so I suppose it is okay. And this essentially shows that it is not possible to have open 0, open 1 as image of closed 0, open 1. If f is a continuous function from R to R. And it actually happens that in case if it was a function from G from closed 0, open 1 to R, if we didn't have the whole R, this is also possible. So that's something for you to think if you get it good. Otherwise you can get help from some of your friends or seniors. Okay, and the time is almost 12:30. So do you want to see more, or we can do, if you have some questions we can ask that, or whatever is fine, sir. So what is
Yeah.
that we usually do?
Uh, we can have a short discussion, and
Yeah, okay.
because many people are left because they have short of data maybe there.
Yeah, possible. Okay. Okay, so if you have anything to ask, you can ask. I mean, from whatever I have covered till now, or something else from real analysis, or something else from somewhere else in mathematics, other than, of course, PhD level.
So students, so participants, it is the time for you to ask your doubts. You can comment. Your comments about class are all are welcome. You can.
Yeah, and please let me know if it was too slow, or I don't think it was too fast. So, I mean, we were only able to cover, say, 6 questions or something.
Yeah, it's not a problem because we have discussions in between. That is more helpful for students, I think.
Okay. Please tell problem books for real analysis. Actually, if you take any of the standard books, it would have some problems, like you consider Rudin or Patil Shabat, or, and there is actually a book called Problems in Mathematical Analysis, that's actually a three volume book by Kajor and Novak. So you can either look at that, or I think there is something called examples by Gelman. So yeah, there are enough. Yeah, Novak. Yeah, that's actually a book which is recommended by many. And usually, as I said, most of the texts have enough problems in the back. So yeah, any more suggestions, questions?
Participants, you can unmute yourself and express your comments and doubts. Please come forward.
Oh, actually, Sanchita. Oh, thank you for that.
Sir.
Yes.
Sir, I have a
Yes.
doubt.
Yeah.
At the beginning,
Huh.
at the beginning, you said that f of x is equal to x square sine 1 by x is uniformly continuous on any closed interval, right?
Yeah, that's because it's a continuous function, right?
Yeah, that's fine, sir. But when x tends to infinity, it goes asymptotically to the line y is equal to x. So my doubt is whether it is uniformly continuous on R.
Why do you say that it is asymptotically equal to x? It's not asymptotic, right? It actually oscillates between x and minus x, or x square and minus x square, right?
Square sine 1 by x.
Okay, so your function is x square sine x, right?
Sine 1 by x.
X square sine 1 by x. Oh, x square sine 1 by x. Even this, you see, sine 0 is 0. Oh yeah, that may actually go to 0. Yeah, that is my mistake. Okay, okay, maybe that's, I'm not sure. Let me see. That may actually go to 0. Okay, I'm not sure which one of this. Yeah, this is actually, as you said, is asymptotic, and it goes to 0. Yes, my mistake. Sorry. So this will be something like this, right? Right.
Yes.
Yeah. Right. Yeah. So it is actually uniformly continuous in whole R. Yeah. Thank you for pointing that out. Yeah, I was actually thinking that it is x square sine x or something. Yeah. Thank you. Yeah, that's nice catch.
When x goes to infinity, it is asymptotic to y. Y is equal to x.
Yeah, it's asymptotic to x. It's asymptotic to
The line y is equal to x.
sine 1 by x, which is equal to x times 1. Yeah, so it is y equal to x. Yeah, maybe so. Yeah, true. It is asymptotic to y is equal to x. Yes.
So
You can see what I'm writing, right?
Yeah.
This is what you mean, right?
Yes.
So this is equal to x times sine 1 by x by 1 by x. And this limit goes to 1. This limit goes to 1, right?
Yes.
Yeah, hence you get it as 6. Yes, thanks. So in both, I mean, anyway, it is actually uniformly continuous.
Thank you.
Right. Yeah, thanks for the catch. Yeah, so my mistake was I thought something like it is x square sine x or something. If it is x square sine x, it is bounded even here. So there is no point in taking x square sine x. Yes, nice. Anything else? Any more questions?
Okay, others, if you have any comments, you can make it now. So Ria
non-continuous. So Ria is question. Any non-continuous function which satisfies f of x plus y, f of x plus f of y. Okay, I think you saw the next question, right? Yeah, that was actually my next question. So you have the property f of x plus y equal to f plus f of y. So if you know linear algebra, you may know this as some linearity. If we are not considering f of x equal to a times f of x. Okay, so this is, and if you consider real numbers just as a group over addition, then you can see that this is the homomorphism property. So what I wanted to say is this need not imply continuity. So you can actually have a function, a lot of functions such that it satisfies f of x plus y equals f of x plus f of y, but it is not necessarily. And as a side, let me ask one more question. You have real numbers, right? Real numbers as a group with addition. And you have complex numbers with as a group with addition. Are they isomorphic? So as group with addition. As we don't have time, I'll just say the answer. The answer is yes. And if you can figure out the isomorphism, you will get the answer, Ria, about f of x plus y is f of x plus f of y. Is it continuous or not? The catch is, no, I won't tell you the catch. So that's actually nice. I think you had told the continuity of tan x on Q. Continuity of tan x on Q. You see, tan x is not continuous only at odd multiples of pi by 2, right? That's how it is, right? If it is not an odd multiple of pi by 2, then it is like, it is continuous, right? Reshma. So, and pi by 2 luckily is not a rational number, hence we kind of do that. Reshma, is this fine? All we have to do is inverse image of open set is open set, right? So you consider this tan x like this, and you consider any open set, you will see that here also it is an open set. If you are considering some open set which contains pi by 2, the thing is you have this open set, which will be essentially, here it is an open infinity, open a comma infinity, and here you will get something like minus infinity comma b. So this is open. So inverse image of open set will be open. So hence you get that tan x is continuous in Q. And can we give its function by formula as we do explicitly? Actually not explicitly. I can only, okay, I'll tell you the catch. You have to see real numbers as a vector space over rational numbers. So that's the clue. If you get this, then you can do both. Okay, any more doubts or clarifications? Thank you, Nimi. Thank you for coming.
We are almost towards the end of the session. I think there is no one to comment or ask any doubts.
Yeah.
So let me express my thanks and gratitude to Hari. Many people are responding that the class is very wonderful and really inspiring and helpful for them. Sending me personal messages that please arrange one more session. So if possible, we can think about it in future. Okay.
Yeah, we will see.
And I feel that the session is very remarkable because throughout we have interaction. Usually we used to have only interaction towards the end, but today we have interaction throughout the really a nice experience. I think it is very worth for the students, those who are seriously approaching mathematics. I feel very happy that many of the students from participants are actively involving in the discussions. So it is a very positive sign, I think. I would like to express thanks on behalf of the entire team. And once again, thanks to everyone. So we will wind up here. We will have another session on next weekend. So okay, thank you all. Thank you.
Okay, so thank you, sir, and thank you everyone for coming. Thanks.
So let us wind up this session here.